The title of our tech talk today is Construction Sequence, Creep, and Shrinkage Analysis of Concrete Buildings. I'm Alan Adams. I'm Chief Structural Engineer and Senior Product Manager here at Bentley Systems. The tech talk today is a little less formal than most. I want this to be a little more interactive, so please submit your questions and comments, and over the course of my presentation, if we have time to answer them at the moment, we'll do that. Otherwise, we intend to devote a significant amount of time at the end during the question and answer period to answering your questions. So again, please feel free to submit those questions and comments. We often talk about the analysis of lateral forces, wind and seismic, and all of the things that need to be considered so that we can obtain a proper analysis. Today I want to turn our attention to some conditions that impact the suitability of the vertical analysis. Maybe some things you've maybe haven't thought about before, maybe some things that you've pondered before, and in many cases maybe some things that you're already doing. So let's start with some fundamentals. Axial elastic shortening, delta, is a function of the axial load, the length of the column, the cross-sectional area, and the elastic modulus, E. And note in particular in this equation that P over A represents the stress in the column. If the stress, L, and E are all constant in all of the columns at a level, they will all shorten the same amount. But if any of these differ from one column to another, you're going to have differential shortening of the column. For example, in this model, all columns have the same area, and I loaded all columns with the same axial force. So they're all uniformly loaded at any given level, uniformly loaded, the stress is all uniform. And as a result, all of the columns within a given story are shortening the same amount. The columns are all shortening, the beams are just dropping. So the beams aren't impacted by the shortening at all, other than they're just in a lower location than they originated at. In contrast, in the model on the right, the end columns are loaded with roughly half the load of the interior columns. And this is a real common condition for, say, a corner column or an edge column. As a result of the differences in the loading, the interior columns are shortening more than the end columns. And this forces a different curvature into the beams. And so the beam design forces are going to be different between these two conditions. And to further illustrate what's going on here, it might be helpful to animate these. So the model on the left shows the columns uniformly displacing under the equal loading. The beams are just going along for a ride, and the displacement and the curvature of the beams is purely due to the beam loading. The model on the right shows the columns with differential shortening. The beams are impacted by this. Their displacement and curvature are a function of both the beam loading and the column shortening. So you can clearly see the differences between these two models, one where there is an issue with differential shortening and the other where there's not. And the differences between these two models, the design forces, design moments, could be very different in both the beams and the columns. So what I want to take a look at first, or what I want to look at now, let's actually look at the moments. Let's look at the gravity moments in these two frames. So again, I grabbed those results in the model on the left. It was set up so there's no differential shortening in the columns. In the model on the right, there's unequal loading, so there is differential shortening in the columns. And you can see the differences in the beam moments between these two. And if you'll note, at the lower levels, there's not as much difference, but as you get more towards the top, then the differences tend to be, they tend to get greater as you get towards the top. And so I've grabbed the top set of moment diagrams from those two models so that you can more clearly make the comparison. Notice in the midspan, there's not a whole lot of difference, but it's those end spans that are particularly impacted. And in this case, the moment on the right is 8 degrees or 8 kip feet different, and the moment on the left of that same span is 8 kip different. So there's a redistribution of those moments between those two. So if you don't take into account the impact of differential shortening, you could be underestimating or overestimating the design moments in the beams. And similarly, the moments in the columns are impacted. And so the takeaway from this is that differential column shortening has an impact on the distribution of member forces. And I think that's pretty obvious, but I just wanted to go through this exercise just to get us thinking about that, what the impact is of this differential column shortening. And anything that causes or changes the column differential shortening is going to impact those design forces. And so what I want to talk about now are some things that will have that kind of impact. So first of all, I want to talk about the traditional analysis, how we analyze structures, how we create a model and analyze and use those design forces. So typically, step one, as we use our software, we create this analytical model. We define the geometry, we specify story heights and base spacings and member properties, and we create a model of our entire structure. The next step is we specify our loads. So we specify, for example, our gravity loads, and we place those loads on this structure, and then we analyze the structure. And we get the design forces, and we use those in our design. But the question is, how realistic is this? Is this really the way a real building is loaded? It's all in place, and then it's loaded, and then deflects? What I want to do is start with live load. Typically, the building is all constructed. The real building, it's all constructed, and it's all in place. And then there's this celebration, and there's this open house to celebrate that this building is completed. And then the tenants move in. And so the building deflects. So for live load, that traditional analysis is correct. The building is in place, physically is completed and in place, and then the live load, the tenants, are applied to the structure and it displaces. So that traditional approach for analyzing the live load case is certainly appropriate and proper. But let's talk about dead load, because that's different now. In the construction of a building, they build the first floor, and then they remove the shoring, and so immediately the loads on that single floor are applied and the structure displaces. And then they come and they build the next floor on top of that. And the column shortening now is all built out for this next level. It's all level and it's in place, and they remove the shoring, and that story displaces. And the impacts at the load from that story now are also loading the story below. And so forth and so on. The story is built. It's immediately loaded with the self-weight. And when I talk about dead load, I'm really talking about self-weight, which is the majority, especially in a concrete building. The self-weight is the majority of the dead load. And so on and so forth. We build these levels. The load immediately takes effect, and it induces those forces into the members until we finally get to the roof, and we have this completed structure. But that's entirely different than the way we looked at live load, and that's entirely different than the way we analyze structures. For the dead load, it's not the case where the entire structure is in place and then we turn on gravity and suddenly we get all this displacement. It's actually applied step by step or stage by stage. And so what we call a construction sequence analysis, an analysis taking into account these steps, may be necessary for dead load, certainly something that needs to be considered. I want to step back. I know this, I indicated this is about the vertical loading, but I do want to address quickly here wind and seismic loads. Again, we create a model of the entire structure analytically, and then we apply wind and seismic and do the analysis. In the real world, that's the way a real building behaves. The building is in place, presumably, before the design wind and seismic loads strike that structure. And so our traditional analysis of creating a model, then applying the loads, and doing the analysis and using those results for wind and seismic forces is in line with what's happening in reality. And so doing some kind of a construction sequence analysis is not necessary for lateral loads. Now, for a very tall structure, there often is a concern that some high winds or an earthquake of some magnitude could strike, and you certainly could build intermediate models, analyzing and then designing accordingly. But in general, an elaborate construction sequence analysis, I wouldn't consider to be necessary. So what I want to do now, so we've talked about construction sequence analysis. I hope you understand perhaps the importance maybe of looking at that. And what I want to do now is just briefly show how that can be accounted for in software, and in particular I'm going to use the RAM structural system to do that. And so I've created this 9-story concrete model, and here's the entire model. It's got both gravity and lateral framing, but what I'm going to focus on is the lateral framing, the moment frames around the perimeter of the building. And in order to perform a construction stage analysis on this structure, it's very simple actually. What I need to do is I need to go to the criteria and specify the construction stages. And so what I intend to do here is to indicate that each story is its own stage. And so I merely say the number of stories per stage is 1. And I could change that if I wanted to lump these and say, to speed up the analysis because I have a very tall building or for whatever reason, I could indicate that let's assume that the second and third story are one stage, and then the fourth and fifth story are the second stage, and so on. So I could lump these stories into groups of stages, or each stage would be a group of stories. But in this case, it's only 9 stories. I'm going to specify that each story is its own stage. So I'm going to generate those. So now we see second floor is stage 1, third floor is stage 2, and so forth up to roof being stage 9. And so that's in line with what we saw earlier as I was showing the loading and deflection one story at a time. This is the kind of analysis we're going to get. It'll analyze the second floor first, then it'll add the third floor model and analyze the second and third together. And then for the third stage, it will add the fourth floor and analyze these together, and so forth. So simply generate, I merely need to generate the stages. Now we also have the ability, if you want, to assign individual sections of the model to be in a different stage. The program has the ability to do that. Because of time, I'm going to forego that, and what we're going to go with here, which is more typical, is each story is its own stage. Now I also need to create a load case that represents that construction stage analysis. So I'll give it a label. I will select construction stage analysis or construction sequence analysis. Same thing, different terminology. and I'll add that. And right now we're only going to consider the stage analysis. In a few minutes we're going to talk about the time-dependent effects. We're not going to do that right now. For this one we're simply going to do a stage analysis. And what I have is the option here. I can tell the program that I want this stage analysis to take the place of my traditional dead load analysis. And if I select this box, then in the subsequent design modules, for example, if I go into RAM Concrete and do the concrete design, in the combinations that are generated there, for dead load, the program would use this construction sequence analysis result values rather than the traditional dead load results. But for our demonstration here, I don't want to do that. I want to keep both the dead load and the construction sequence analysis as separate cases so that we can take a look at those. So I've created this construction stage analysis load case, and just to note, at this point I could also do the wind and let me go back in here. I could also create the wind and seismic and dynamic load cases and all of that, and those would be populated here. But that's not the point of my presentation today. So we're going to just stick with these gravity load cases that we have here, the dead, the live, and the construction stage analysis. Now I analyze the structure. I select those three cases and complete the analysis. And now we can take a look at the results of that. So the first thing that I want to do is look at the displaced shape. And so right now what we're seeing here is the dead load case. And we can animate that to better see what's going on. And we see that the interior columns are deflecting more than the corner columns, so we're getting that differential column shortening effect going on and impacting the beams. Notice the magnitude of that displacement compared now to the construction stage analysis, and there's quite a difference, especially as you look at the top of the structure. So this construction sequence analysis really does highlight that there's a difference in the behavior rather than the traditional dead load case. And so we can take a look at those, and obviously the reports can give us the values of the magnitudes of those as well. Okay, the next thing I want to do is I want to take a look at the member forces, and in particular, let's take a look at here's the shear here, but let's take a look at the moments, and let's take a look at the moments. To clean this up, let's look at the moments in the beams. And we're going to scale up here so we get a better view of the diagram. And we're seeing the shear here. Let me get it to go to the moments. There we go. Okay. So what we're seeing here are the moment diagrams and the moment magnitudes for this structure. And we can do the same thing. So that's construction stage analysis. And here's the traditional dead load. And what we can do is we can compare those results. So that's how simple it is to do a construction stage analysis. These results now are available for use in the design. So let me go back to the presentation.
I have a few questions that came in here on the construction stage analysis here in RamFrame.
Okay.
First question, is RamFrame adjusting the length of the column braces wall heights between each stage to put the top of the steel and concrete at the ideal elevation?
And Blunt can correct me, but I believe that yes, it is, that when it creates that next stage, it's putting it back at the elevation that the floor is supposed to be at, and so it's correcting for the shortening that has occurred in the previous analysis.
Correct. And then a second question here on column shortening. Do the column shortening results take into account the percent of reinforcement, or is it simply PL divided by EA?
At this point, it does not take into account the contribution of the reinforcement. We've had some discussion about that. That question has come up, and we certainly need to do some research on that to see what contribution that might have. Traditionally, this is the approach that's been taken in a construction sequence analysis, and certainly that's a valid question. What is the impact of the reinforcing? Hopefully, we can, through further research and experimentation here, come to a conclusion on that. Okay, so I appreciate the questions there. So what I did is I grabbed those results from those two analyses. The one on the left is the traditional analysis for the dead load, and the one on the right is the construction sequence analysis for the dead load as well. And as you can see in the traditional analysis, well, in the traditional analysis, that differential shortening is significant. And in the construction sequence analysis, the differential shortening is less significant because it keeps getting built out as you go up the structure. And what you were seeing here are the design forces are very different. Before I move on, I'm just thinking of the previous question, and it's interesting to note that when we do structural analysis, we base the stiffness of the structure on the concrete section properties, and historically we haven't taken into account the contribution of the reinforcing at all, and how it stiffens the structure in the analysis. And so that's an interesting question that affects not just construction sequence analysis, but all analysis that we do. When we input the stiffness and the section properties and all of that, it's very rare that we would also include the stiffening effects of the reinforcement in our structural analysis model, because we don't know what it is until after we've analyzed the structure. So historically, we've ignored it for all aspects of our analysis. Just a thought that occurred to me. So back to the presentation here. So we look at these numbers, and to give you a better sense, again, we're just looking at the top level here, and we see the differences in the moments between the traditional analysis and the construction sequence analysis. And I think that the conclusion here is that it might be necessary to consider for our dead loads, that the impacts seem to be real, and it's something that we do need to take into account. And certainly for taller structures, if you have a wide variation in your axial load P, or if there's changes in the cross-sectional areas of your columns due to some architectural constraints, then a construction sequence analysis might be advisable. I want to move on now to another topic, that of the time-dependent effects. Because these effects that we've talked about, the axial shortening, that's the elastic shortening, that's an immediate shortening. It's not a time-dependent effect. But I want to talk now about the time-dependent effects, in particular creep, shrinkage, and concrete strength, which impacts the modulus of elasticity.
Say, Alan, can I jump in here?
Sure.
A question came in regarding the last slide. The question was, unless the building is really tall, the effect of axial shortening should be too small for consideration. Is that correct?
If you have a short building, that's the case. What we're looking at here is a 9-story building, and so you'd have to decide if that was enough for you to worry about. But certainly for the shorter buildings, 2, 3, 4 stories, probably not a problem. The nice thing here is, as you can see, it's very easy to investigate, and I would encourage all of you to investigate not just this, but anytime you have a question, well, what would happen if I did this, and use your software to learn the impact. The software allows us to do that. Historically, we did so much by hand, and if we had computers, they were so slow we couldn't do a thorough investigation. But that's not really the case anymore. We have these tools, and I would recommend that you take a look at a shorter building and look at the impact of construction sequence analysis and get a sense of where that begins to be a problem. So creep is a slow change in the length of the column or the beam. It's a slow change in the cross-section over time. The concrete isn't truly this rigid material that we think it is. I mean, it is, but it exhibits this creep that can occur over time, where the column shortens, the cross-sectional area flattens out. Shrinkage, on the other hand, that's a function of, in particular, the water content of the concrete. And as the concrete hydrates, the members, they shrink. There's a reduction in the volume over time. And then finally, we're all aware of how concrete gets stronger over time as it cures. Well, that means the modulus of elasticity is getting greater and greater over time, and that has an impact on the stiffnesses of the members. So as these changes all occur, they're changing the stiffness of the structure. They're changing member lengths, and as they occur, there's a redistribution of the forces in the frame members. And so I want to talk about how now in ram frame we can handle those. And so we're going to go back to the model here, and now what we need to do is add to some criteria. So the first thing I need to do is, in addition to my stages, I need to indicate how long, what the period is, the duration is of each stage. Because now we're talking about effects that are dependent upon the time. So under the duration tab, I'm going to indicate what the duration is for each stage. And so maybe they're pouring the floor once a week. So the duration of that stage would be 7 days. And so I'm going to assume that's the case. Maybe it's 5 days, maybe it's 10 days, depending on, or whatever, depending on the size of the structure. And I could have different values here for different stages, depending on like the size of the floor and whatnot. For my demonstration, I'll simply go with the 7 days for the duration of each stage. So I simply indicate that duration. And then I also need to specify a material model that is used, the technique that's used to account for creep and shrinkage and change in elastic modulus. And we've implemented 3 distinct methodologies, and each methodology requires its own set of information about the construction process, about the concrete. Some of the information is relative to both creep and shrinkage. Some is particular only to shrinkage. And there's things like the drying start time, how many days, what's the cement content, what's the percent of fine aggregates. And so we specify this information so that the appropriate methodology can be performed. And by default, all of the members are given this default value. But if there are some members for which any of this information is different, I can add another set of properties. And so I could change this to a new set of values, whatever it might be. So now I have a new set of values, and I can continue to add additional sets of values. And then I have the ability to assign the particular material model property set to any given member or sets of members that I so desire. But again, to keep this demonstration simple and because of the shortness of time here, I'm only going to consider that all of the members have this particular set of material model properties. So I've got that established, and now I need to modify my load case that I created previously. So now I tell the program, now consider these time-dependent effects, and I can select any or all of those to see what their individual contribution is or their cumulative contribution. And I indicate which technique I want to use, whether it's ACI 209R, CEB, MC99, or Model B3. I select the technique that I want used for this analysis, and I say OK. And now I can perform the analysis that includes not only construction stage analysis, but also creep and shrinkage and material strength changes. So I performed that analysis, and now once again, I can take a look at the results. Construction stage analysis, here's the displaced shape, versus, we still have that dead load case that we can compare it to. And then in addition to the displaced shape, again, we can look at the member forces and apply those. So here we see the moments, and so we can compare, there's the dead load versus the construction stage analysis, and we can compare those results. Now we can also compare the results of the analysis with and without the creep and shrinkage. If we just grab the results and we can compare those, and that's what I'm going to do. So I want to express right now how easy it was to take these effects into account merely by setting up that information and setting up that load case as I indicated. So it's merely that simple. So I grabbed those results first of just the construction sequence analysis by itself, and then the analysis that we just did where it includes the time-dependent effects, and we can see those side by side. Now, one thing that's interesting here is that it's not necessarily at the top where the difference is, where we're seeing the biggest difference. In this case, it's more towards the middle of the structure where we're seeing some slightly different values, not as significant as what we saw between the dead load case alone and the construction sequence case. That had a bigger difference. Now what we're seeing is a construction sequence analysis with and without the time-dependent effects. So though in this 9-story building, there is some impact, but it's not particularly significant, and the impacts are felt throughout the structure, not focused particularly at the top of the structure.
Alan, I have a question here on time-dependent effects.
Yes.
The question is regarding time between stages, which is more conservative, shorter time between stages or greater time between stages?
The longer the period, the more the effect of the shrinkage or shortening or strengthening there will be. And so I would expect that the longer the period you have, the greater the impact you would see. And so one thing I didn't point out is I set up those stages, but I could have set up one more stage and indicated that it was out at some time, say 5 years from now, and then I could actually have used those results of the creep and shrinkage and concrete strengthening that had occurred over the next 5 or 10 years and looked at those effects. Now, typically that's probably not necessary because most of the effects are going to happen in a very short period of time over the first few days. And so looking at very long periods of time, the impact of what you saw what you would see in the analysis a month from now versus what you'd see 10 years from now wouldn't change very much, because the changes in creep and shrinkage are very quick in the initial stages of the concrete, and then they plateau out as time goes on. But in answer to that question, yes, it would. The longer period would have more of an impact, but maybe not significantly more. Probably not significantly more. Yes, go ahead.
Sorry, Alan, multiple questions came in here on crack section factors that are defined in RAM Modeler and how those come into play with the time-dependent creep and shrinkage and cracking. Can you speak to that?
Yes, right now the program will apply the cracking factors, and we had quite a discussion when we presented this same webinar yesterday for India and Asia and Australia, for that part of the world. That was quite an item of discussion that came up during the presentation. We've had a lot of discussion about it here in-house as well, and we're trying to determine what's appropriate. Right now, the program will apply those crack factors. But the argument could be made that in these early stages, when we're looking at these effects, the cracking probably hasn't occurred because we haven't yet seen the full loading on the structure to create the cracking. And so the argument could be made that for this analysis, the factors shouldn't be applied. And I can appreciate that argument. I think what we're probably going to do is probably provide the user with a second set of factors that they can specify be applied during this type of analysis that may be more appropriate rather than the traditional crack factors. But right now, that's what we're doing. We're applying the crack factors. What we're doing is conservative. The question that would now the question that would now arise would be: are we seriously over conservative by doing that? And I don't know the answer to that. So let me finish up here. I'm almost done here, and then let's get back to the questions that have been submitted. So we've talked about 3 different types of analysis. We've talked about the traditional analysis, where we create a model of the entire structure and then apply the loads and then do the analysis. And what we found there was that for shorter buildings, that traditional analysis is adequate and certainly acceptable in most cases. That traditional analysis is certainly valid for your live load case, because that's the way the live load actually is applied to a building. The building is erected, and then people and desks and things are moved into the completed structure. And the traditional analysis is certainly adequate for wind and seismic, because even for the time-dependent effects, the wind and seismic loads are transient. They're there only for a very brief period of time, and then they're not there anymore. So typically I would not feel a need to even consider a creep and shrinkage type of analysis for the wind and seismic load cases. So it really is only for the dead load case where this is a consideration, or a necessary consideration. We talked about the construction sequence analysis, the immediate elastic shortening effects, and that should be considered for taller buildings, and then also buildings with transfer girders. We didn't talk about that, but think about a building with a transfer girder. The sequence at which that girder is loaded, and whether or not the framing above is actually helping to support that, acting as a bridge, so to speak, as you go up the higher levels. Are they acting as a bridge to keep that that transfer girder from deflecting more, or are they merely acting as loads on the transfer girder? And the construction sequence analysis will give you very different results on the member forces in the transfer beam. So I would consider it for a building with transfer girders. And then finally, we talked about the time-dependent effects, and I think the conclusion there is for very tall buildings, those should be considered. For intermediate height and lower height, probably not. So those are the analyses that we've discussed here this morning. And what I'd like to do now is finish up with whatever questions and comments have come through. And I'm, as was introduced previously, I'm joined by Blunt Alamdar, who's the principal research engineer, and Carl Gullerud, who is the senior technical support engineer. And so if you have any additional questions, please feel free to continue to submit those, and we'll answer as many as we can over the next few minutes. And if we can't get to all of them, then we'll try to individually reach out and respond to your questions. So, Carl, go ahead and let us know what's come in there.
Yeah, we have lots of good questions and comments here. First, is construction stage analysis applicable for gravity members?
If the members are continuous, like would be the case for a concrete structure, then I would say that's the case. If the gravity members are not as stiff as the frame members, then the impact on those is not going to be as great, because even though the frames are deflecting, if they're stiffer, they're going to attract most of that effect, and the smaller gravity members are going to more or less go along for the ride, but they would be impacted. If there is a concern there, what I would suggest in the RAM structural system is model all of the gravity members, at least the ones that you're concerned about that effect, model them as frame members, at least to look at the gravity load, that gravity analysis, and see what the impact is. But yes, because of continuity, gravity members could also be impacted.
A few questions came in on how slabs affect the analysis. So I'll start with a general one. Does the shortening of the columns impact slab forces? Maybe speak to one-way slabs and two-way slabs?
Because the slabs are continuous with the columns, then that would certainly be the case. The slabs are essentially acting as beams, and so that would have an impact. Because they tend to not be as stiff as beams, the impact would tend to be less, but yes, it could have an impact on your slabs. And in the RAM structural system, that if you've modeled your slab as a two-way slab, for example, and you've specified that it's semi-rigid diaphragm, RAM frame will do an analysis, and slab now will be included in the construction sequence analysis. And if you indicate that you want to do those time-dependent effects, the slab will also be impacted by those effects, and as a result, the forces that you get in your slab will reflect those effects.
And then a slightly more detailed question on slabs. If you have inclined columns that impose diaphragm forces into the slab elements, do the construction sequence analysis results take into account the increasing diaphragm force during construction? And then what kind of slab modeling technique would you use?
Again, if you've modeled the slab as a semi-rigid diaphragm, the program's going to mesh that. Those slabs will be part of the analytical model, and so in stage one, for example, the slab of the first floor will be included in the model because it's it was modeled as a semi-rigid diaphragm, and the impact of the construction stage analysis will impact forces in the slab and in how the slab behaves in pushing back on those sloping columns, etc. So yes, that's all taken into account in the analysis.
And then one final question on slabs. Can the construction sequence and time-dependent effect forces and moments be imported into ramp concept?
Carl, you might actually be more capable of answering that question than I can. Let me just quickly, if you select the option to use the construction sequence analysis results in the place of the dead loads, then what gets imported over to concept is, for the dead load case, is the results of the construction sequence analysis. So I don't know, Carl, if you have anything to add in regard to that.
Nothing to add there. That's actually what I was hoping you would say. Wasn't sure how RAM Data Access handled that, but that's great.
Alan?
Yes, Blunt.
I also clarify one thing that during your presentation, I guess there were several questions posted regarding the reinforcements, cracking of the cross section, etc. How those are considered in construction sequence analysis in RAM frame. Maybe it is good to clarify one point, that the analysis we provide in the program is actually targeting the response of the structure in the early stages. And he also clarified that because of that, cracking in the members may be not occurring at that time. And this is actually the type of analysis we have in the program that is targeting the earliest responses of early stages of the structure. Regarding the long-term deflections, like 5 years later or 30 years later, we can consider that kind of analysis as well in the program, but we don't consider the impact of reinforcement or cracking of the concrete members over the next 20 years, let's say. At this point, the one solution would be to run the model in RAM frame, and as Alan indicated, if you use that option, at the end of the stage analysis, you have the results. You can export those results into the concept, and inside the concept, actually, you can, or one engineer can run a more rigorous analysis that consider the cracking of the cross section, the relocation of the centroidal axis, etc. That kind of solution can be actually adapted in the program using both RAM, frame, and concept.
Good, thank you, Bilan. I appreciate that clarification.
We had a few questions on construction stage analysis and the use of the dead load case. In RAM frame, long-term effects are only applied to dead load, correct? We'd want to include a portion of the live load similar to slab long-term deflections.
That's something then that we need to consider as a future enhancement, and I think that would certainly be doable and something that would certainly seem valid. Some of the live load would be in place long term. Now, keep in mind that if we're only looking at the construction stage until the building is constructed, I guess the live load that would be of consideration there would be just the construction type of live load that might be in place, but certainly not part of the permanent live load. That hasn't really occurred until after this these early stages, the construction stage is completed. But But we will certainly keep that in mind as a future enhancement to allow some portion of the live load to be included there.
And then a question on time duration. Has a rule of thumb been established regarding time duration such that beyond a certain point the effects being considered can be considered negligible?
If I don't know the answer to that. I don't know if Balan does or not. I'm not aware from a practical standpoint of any rule of thumb that would indicate when the time no longer makes a difference. I don't know the answer to
that. In the software, are you able to model tension stiffening in concrete? I think that goes back to time-dependent shrinkage.
Carl, the answer to that question is no. We don't address that behavior in the concrete.
We talked about cracking and members. Is it on the horizon to take into account the reinforcement and cracking of members and do an actual nonlinear analysis in RAM structural system?
After our presentation yesterday, and the discussion that came out of that, Balant and I had some discussion, and that's certainly something that we would like to do, is to automate that whole analysis. And rather than the users having to apply crack factors and figure out, okay, is this appropriate for the construction stage? Is it not appropriate? We would certainly like to perform the analysis and automate the whole application of the cracking factors. Answer is yes, that's certainly something that we want to do. We don't have a timeline for that at the moment.
Got a comment and a question here. It would be very useful to see forces and deflections at the end of different stages and at certain times. Is the deflected shape that's shown in RAM frame at 50 years?
So the deflected shape that we're showing is at the time, in a case of just the construction sequence analysis, that's an immediate shape. When it includes the time-dependent effects, what's shown is at the end of all of those stage durations. At that point, that's what we're showing. So, like in the case that I indicated, I had 9 stages, and each stage lasted 7 days, so that's 63 days. So the deflection that we were seeing was the deflection approximately at 2 months out when the building now is complete. Now, if you wanted to see what the deflections and forces were out at some future time, say 5 years out or 10 years out, you could create an additional time step, and then what you would see is for the final result, what you would see is out there at that 5 or 10 year step. Now, we don't provide at this point, since this is a new feature, there's a lot we still want to add to it, but at this point we don't provide a way for you to see the results of any intermediate stage. What I would invite any of you that are interested in that, please contact us and tell us why you want to see those intermediate values, because that represents some additional work on our part to expose those and the interface to look at them and manipulate them. And we would like to understand what the need is for looking at those intermediate values, and then we can assess the amount of resource that we want to devote to exposing that information. So I would invite those of you that are interested in that, let us know, educate us, and let us know what it is you would do with those numbers and results.
A question on some of the examples that you showed, Alan. In your analysis, were the column sections all the same, both internal and external?
Yes, in my example, all of the column, I used the same column section property for all of the columns. So I was not varying the area, only the axial force was being varied, so that the stress was varied between the columns, but the area, the section properties themselves were constant for all of the columns. And that's often the case. Ideally, we would size those end columns to be smaller because the gravity load is smaller. But those are precisely the columns that take the bulk of the wind and seismic forces, and so they need to be bigger. And so it's very often the case that the end columns and the interior columns are the same size because of wind and seismic force requirements. And as a result, under the dead and the live load, under the dead and the live load, we get those the differential column displacement, because now the interior columns have a higher stress than the exterior columns. One thing I would like to do is I'd like to give Blanc a chance, because I know this came up in yesterday's presentation and there may be some questions here. If Blanc could just briefly touch on the different concrete models that we use for creep and shrinkage and what those are about. We give 3 choices, but Blanc, if you could just kind of enlighten us briefly on what those models represent and how those came about.
Sure, Alan. As you actually showed in your presentation, that we have 3 different concrete models. Based on these models, we calculated creep and shrinkage effects as well as changes in elastic modules of concrete. These models are ACI 209R 92, CEB MC 9099, and model B3 from Professor Bazant. These models actually extensively mentioned and in one of ACI design documents, ACI 209.2R08. And we usually for the material response, most of the studies actually based on some experimental results and then some numerical methods developed, and all those numerical methods or approaches calibrated based on the experimental data. So these 3 models actually kind of calibrated results based on the experiments. And ACI is mostly obviously in the United States. CEB model is one model from Europe. And B3 model, I guess, generally well known, and it's considered much more complex but much better results it produces. And obviously, the engineer choose one of these models based on their jurisdiction or their local design regulations. For the time being, this is the only models we offer. We are hoping that we're going to add more models, especially from foreign design codes. And we're also considering the option of that the engineer can directly provide their own creep and shrinkage data, and we directly use that information in this analysis. I hope this clarifies your question, Alan.